So now I think we can come back to class. Good morning, ladies and gentlemen. Get me chalk. Get me chalk. So I want us to wind up with, make sure that you maintain maximum silence and discipline. These are usual things. The problem, when I tell you the truth, you don't want to. Now, Christine, you're supposed to look here. So yesterday, Joan was like, no, we did not get well. How human took us through a certain law called Hooke's law. So I've come back, and now I want it to go on record. Joan Mwisho, I want it to go on record, such that the next time you say, human, you did not do it, I refer you to the video. So first and foremost, Hooke's law, I said that we look at the statement of the law. So Hooke's law or Hooke's law. Listen, I will chase now some people. You go and study from the other streams. If you cannot contain your arrivalism, then you will go to other classes. So I'm saying that one, we look at the statement of the law. We look at the statement of the law. Which statement is stated in literature, in English? It is stated in English. Human, I will slap you. I will slap you too, mama. What is your problem? So I'm saying that we first of all look at the statement of the law. We state the law in English. What did the man discover? And what did he state in English? These laws are supposed to be stated, one, in English, two, mathematically. Because it is from the mathematical statement that we generate or that we carry out an experiment to verify. So first and foremost, how does the law state in English? Joan Mwisho, I have people here who I know that they can try to also go back and give testimony. Wait. Hold here.
Oh yeah.
No, I have to get the audio on. Just hold. Listen.
The extension of an elastic material is directly proportional to the applied force, provided the elastic limit.
The law states that once again.
Of an elastic material is directly proportional to the applied force, provided the elastic limit is not exceeded.
Take the microphone to Patience. She also states the same law. Using your own book.
No, mega. You press here.
Patience. Get serious. Patience, I will slap you. Oh, don't press anywhere, just hold it close to the lips.
Hooke's law states that the extension of an elastic material is
The rest keep
directly
quiet.
pro- prof- eh, proportion to the applied force provided to the elastic limit.
I don't think there is provided today. Read it again.
Hooke's law states that the extension of an elastic material is directly proportional to the applied force provided the elastic limit
Do you have the notes in your book? Patience, don't make me again misbehave and it goes on record. I'll beat you. Now, where is the one that got over? Who else? Read through how the law states. Put here.
Hooke's law states that the extension of an elastic material is directly proportional to the applied force provided the elastic limit is not
Now,
extended.
you are at stake. You are risking coming back after issuing these notes and you don't have them. I will now misbehave. Because now you think you are here to help us. If you don't want to come to school, please remain at home. So Hooke's law states that, we say it states that the extension of an elastic material is directly proportional to the applied what? To the applied force provided the elastic limit is not exceeded. I mentioned here when I was answering the question there that when you are stating the law, you look at which one is going to bring what. Now, in this case, the force is going to bring the extension. So that force that brings the extension it brings depends on the force. So in other words, the extension is directly proportional to the force. I think it is. I'm sorry. It's directly proportional to the. Now, when you remove the sign of proportionality, in mathematics you've studied functions, and you know that any variable can vary as either a proportional or directly proportional or inversely proportional. So when you remove the sign of proportionality, you introduce a constant. So it becomes F equals K what? Ke. That for the same elastic material, even when you apply a number of forces, it will give you different extensions, but it will remain the same what? Elastic material. So if you apply a force F equals Ke, making K the subject of the formula, you divide both sides by and you have K as K equals F over E. That for any force that you apply, if you apply the force F1, it will give you an extension E what? E1. If you increase or if you change the force to F2, it will give you an extension what? E2, but the same K constant. If again you change the force to F what? 3. What will you get as the extension? E3. So this becomes the statement of the law, and then this becomes the mathematics of the law. That for any force that you apply on an elastic material, the extension is going to change with respect to the force. If you increase the force, the extension is going to E. But if you reduce the force, the extension is going to reduce. So in our experiment, we shall have the following. We shall have the new length, which we shall denote as L subscript n. Because initially, we shall have the point where the elastic material is as the original length. We record it as L what? LO. Then the new length, we shall have to record it in centimeters, such that we check and see. I think we begin with the force, with the weight that you are going to apply. The mass in G, then you get the new length in centimeters, then you check on the extension, which will also be in centimeters. Now we need to check whether indeed for every force that you apply on an elastic material, it extends as proportionally to the force. Are we together? So basically what we need to carry out this experiment as it appears on page 152, 152, where we have an experiment to verify Hooke's law. Are we there? An experiment to verify Hooke's what? Hooke's law, where we have, this is what we call, what is this? Huh? Who knows what this is? This is? I always tell you that. It's called what? John, this is called? Not a cramp. It's not a cramp. It's called a clamp. You know the Wanyankole, you don't have a difference between R and L. So this one is a clamp. If there are many like there are two, they are clamps. Then this one here is what we call a retort stand. A retort what? A retort stand. Then what else am I going to use? This is called a spring or a spiral, because of the fact that it is so a spiral spring. Then what else am I going to use? It's called a meter rule. Then finally I will use different masses. So if I offload them from this thing here, this is what we call a what? A what? A mass hanger. Then the other ones are the masses. So we are going to use the ones of 50 grams, which means that we shall keep adding on 50. So we begin by clamping a meter rule and then a a spiral spring. Can anybody load a clamp onto a retort stand? Come and load the nani. You also come and load after she loads this. Load it a little higher. Take it up to the extreme end, around there. Thank you. Then load the second one because we are going to suspend the spiral spring and then we shall have to clamp a meter rule. So now, after we have clamped, after we have fixed our clamps on a retort stand, remember that we are going to use a meter rule to measure those extensions or the new lengths. Because what we shall be reading from here, initially we shall read the original length or the position of the spring before we load it with any mass. We shall read or take the reading of the meter rule, the position where the spring will be before we load it with a mass. Then after putting on masses accordingly, then we shall keep reading the new positions of the spring after we have loaded it with the mass. Then we shall get the extension E from the formula, which is, anybody can tell us how we can get the extension? You girl. Tell us how we can get the extension.
It is new length minus.
You can even come and write. Come with your microphone, please. When you get excited, you lose everything. Extension is calculated from
New length minus original length.
extension is the new length of the position of the spiral spring on a meter rule. When you load a mass on the spring, that spring is going to do what? To extend. So the new length is now that position there. I will get people to read it. Then after, you get the extension from the formula that new length minus where it was before you loaded the what? The mass. That it becomes the extension. So you try out about 5 or 6 masses as we are going to see here. So if I load the meter rule, now let me try to bring this one a little back like this. Then I put a meter rule facing it. I put the meter rule facing the spring such that we can directly read or take the readings. So now I can bring my spring around here. I can bring my spring around there. Then can I have someone to come and tell the class what will be the initial position of the spring? Proceed. Come and also appear before the other audience. Come and tell the class what is the initial position of the spring before we load it with any mass. Of course, a meter rule has 2 sides, okay? One running from top to bottom, another one is running from the bottom to top. So she's going to tell us the position and which side has she used to read the position and why. You want to read? Get a piece of chalk and you inform us. Hold the microphone. Hey, I don't know where you're going to start from. Then hold a piece of chalk. Please don't look at me. Inform your colleagues. Proceed, hurry up. We don't have time. Somebody can help? Any other person? Yes, Evelyn. You're reading the downer part of the spring, right? Yeah. The downer part, yes, where that point is. You read and tell us the reading. You take any reading. From where? From bottom or from top? You're reading the scale from the bottom part, and it is 46 what?
46
centimeters. You record it as L naught. Now let's get another person to read from the top scale. Labera. You are interested in your boys. She read from the bottom scale, then you're going to read from the upper part, the upper scale of the meter rule. L naught, you are still reading L naught because we have not loaded anything on the spring. Are you sure it is 37? Reading from the 0, which is upwards, where the spring is? I doubt. Professor. It is 49. Get me my microphone. You are keeping it as a hanky. Well, now the meter rule has two scales. If this is the rule or the ruler, everybody look here, including patients. It has a scale that runs from 0 to 100 on this side of it. But it also has a scale that runs from 0 to 100 on the opposite side of it, but in opposite direction. Now, this meter rule is placed here in such a way that you have a scale that runs from a 0, which is on this side of the ruler. Then you have a scale that runs from a 0, which is on this side of the ruler. Now, whichever reading that you take, you must be conscious with it. If you take the one that runs from a 0 moving upwards, and you take it like Nshemerere took it as 46. Evelyn took a reading that runs from a 0 upwards, and she took it as a 46. The question is, when you load a mass on this spring, will this distance be increasing or decreasing? Increasing. Will it be decreasing or increasing? Increasing. It will be? Increasing. Are you sure? Yes. This scale that runs from a 0 downwards, from a 0 moving upwards, when you load a mass, will it be increasing or decreasing? Decreasing. Let's check. Evelyn, come and see. If you put a mass here, what shall you have as your Ln here? You are reading here. Hey. $43 centimeters. So the question is it increasing, decreasing? Decreasing. It is decreasing. Which means that now in this case, your extension is not going to be Ln minus Lo. All right? In this case, it will be L naught minus L what? Ln. Then you get your extension. If you take the scale which is running from 0 upwards, but if you take a scale that runs from a 0 and is running downwards, then your extension it will be Ln minus L what? Because this distance will be increasing. Are we together? So when you're taking the readings in this case, you need to be conscious about which scale did you take. If you take the one that a 0 is down, running upwards, it means that your lengths are going to be decreasing. So your extension will be the original length minus the new length. But the best scale to take is the one that it is going from 0 and it's running downwards. So in that case, let us consider Labera's value, which was a 40. But Labera is deceiving. According to me, it is a 55. I don't know whether Labera's eyes have issues. You are reading the one that runs from 0 moving upwards. Oh, so now let us take the one that is running from a 0, but the 0 is up and it is moving downwards. So our original length is 55 centimeters. This part of the spring is at 55 centimeters. So our original length is 55 what? Centimeters. We don't put the original length in the table because for it we record it once. We only put those values in the table that are going to keep changing. Like the new length, of course, every time you put a mass, the new length will do what? Will change. Every time you put on a mass, the new length will change. So we begin with the mass which is 50. We begin with the mass which is 50. When you put in a 50, what will the new length be? So when you put on your mass here, now the remaining part of the experiment is going to be done by human. Let him also teach as I relax. So when we put the mass here, reading the arc here, it is 50 what? We are reading this one here. It is 50. 57. So the new length becomes 57 centimeters. Of course, because the meter rule has decimal points, and we are reading exact one, so you can say point what? 0. Please take over. You are going to keep increasing the masses. No, you remove the masses. I mean the one from the spring. Then you load it. Then you put it back. But you must know what you have loaded there. You tell us how many grams have you loaded?
50 grams.
So when you load 50 plus the one that was there, which was 50, it becomes
100.
So in your table you record, human, get a piece of chalk and begin to teach.
50 grams plus 50 grams I loaded, it becomes what? 100 grams. Then we place our mass hanger. Remember, we count from up to what? Yeah. Excuse me.
Don't hold it. Simply look and read where the last point of the spring is. Sorry.
So it becomes it becomes 60.
What you see is what you record, human. Trust your head.
Excuse me, sir. First, wait a bit. It becomes
Human, what don't you see?
Excuse me, sir.
We are reading this point here. Look at it. Where does it point? It is around 50, 60. What don't you see? I think everything is visible here.
It becomes 60. 60 centimeters, yes?
0.0.
Then we again load our what? Our mass. 50 what? 50 grams.
Record the mass that you've loaded first.
100 plus 50 mass. 150. When we place it it becomes 65.
You know, you must be confident because in practicals you will be reading your results and record them yourself.
It becomes 65.
Now, if you don't trust what you have seen, then who do you think is going to?
0.0. We again load our what? Our mass. When we get the 150 plus 50, two what? 200 grams. When we again place it our mass anger, it becomes excuse me class. Before we exceed, I have made a mistake there in a third reading. Let me first. That is 68. I mean, that is 62. This is 62.
Christine, are you okay? Where are my notes? Yesterday we agreed. After here, you bring and follow me, right? You man, hurry up. We don't have time.
That is 64. 65, yes. This is 65.
You can stop there. Now, you realize that every time you add a mass, a what? A mass, the extension increases. Every time you add a mass here, the extension, it does what? It increases. Now that increment, Hooke says that it will keep on being the same until when you reach a point where the elastic limit is not exceeded. Once it is exceeded, what will happen to the spring? It will break, or it will now lose the elasticity. And once it loses the elasticity, it means that when you remove the force here, the spring will not go back to the original shape and size. Hence, Hooke's law is very far. Now, in the practicals that you will do, you will load up to maybe 250, maybe 300. You read about 1, 2, 3, 4, 5, and 6. Then you plot a graph of this force here against the extension. Now, after you have the masses loaded, the new lengths, they are obtained, then you begin to calculate the extension, which is this length minus the original. So 57 minus 55, what do you get? 43. I've said 57 minus 55. Stand up. Go get some water and come back. So here you get 2 points, then 60 minus 55, 5 points, 62 minus 55, then 65 minus 55, 10 points. So you realize that the extension is increasing when the masses or when the force also is increasing. Now, this is what Hooke talked about, that what you get here is directly proportional to what you load here, only if the elastic limit is not exceeded. Let's wind up with the last parts and then we see what to do. Yesterday we stopped at structures, right? Yesterday we stopped at the structures. So we say that a structure is either a beam or a what? Can we talk? A structure is either a beam or a girder, or it can be a combination. Because we say that a beam is a uniform. A beam is a uniform large straight piece of a material with the uniform cross-sectional area. And then a girder is simply a small thing that is actually put into the beam to make it stronger. Are we together? I talked about the iron rods that are put into beams of the houses to strengthen these beams. So we say that a beam and a girder, a beam is simply a structure which is a little large, uniform, long. Then a girder is something that is fixed in it to make it strong. But a girder can also be can you talk? A girder can either be, you don't have the work. A girder can either be, a girder can either be, a girder can either be a tie or a what? A girder can either be a tie or a strut. A girder can either be a what? A tie or not your necktie, but when you tie something, it becomes a tie. Now, English is also another poor language like the Runyankole. Because the act of constructing a house is called what? Is called building, right? Is called building, right? Then a question, what if a house has been completed in the construction? How would you call that? Again, you call it a what? Now, why? 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 You'll ask your English teacher. This man is trying to oppose. I've said when constructing a house, what do you tell the people? We are doing what? We are building. Then after you have finished your structure, again you say that building there is what? Is mine. So English is poor. This thing here, put off your tie. Where you put it off. This one here is called a what? A tie. Whatever the case, but it is a tie. Now, when I fold it, do this. If I do this, what I've done is a tie. So what is the difference between a tie this and a tie this? So a girder can either be a tie or a strut. What is a tie, ladies and gentlemen? All of you. 1, 2, 3, go. A tie is a girder under what? A girder under tension. When you hold that tie the way I was, bring. If I hold this tie and I tie like you see this, then I hold it like this. It is under what? It's under tension. Are we together? You man, I'm the storyteller. Are we together? If I hold this tie the way I had tied it, then I hold it like this. It is under what? Tension. So it qualifies to be called a what? A tie. Then what is a strut? A strut is a gather under compression. Now, here is the simple task that we are going to see. This roof, as we are seeing it, it is a gather. It is a what? A gather. But now our task is to identify which one is under tension and which one is under compression. Then we look at and say that this gather is a tie. Then this gather is a strut. Examples. So the activity is how do we identify a gather or a strut or a tie? Read for us, gentlemen. How do we identify a gather is either under tension or under compression? How do we tell that this gather is a tie or a strut?
To identify a gather.
Wait.
To identify a gather, remove each gather at a time and observe the effect it causes on the structure.
For you to identify that this structure is either a gather, is either a tie or a strut, as we are going to see the construction, you remove one piece, then see what the effect it brings on the rest of the structure. You pull out one piece. If the remaining part of the structure falls in, if it falls where? If it falls in, then it means that gather has been under a compression, because to compress is to okunyiga. How do you call okunyiga in Runyankole? So when it falls inside, then it means it has been under a compression. So that gather is a strut. Now, if it falls outside, if it falls away, then that one it was under tension, because it is the tension that is pulling it away. Are we together? It is the tension that is pulling it away. So when it pulls it away, then we conclude that gather was under tension. So it is a what? A tie. So it's okay. You can take your seat. Example 1. If you have a structure that looks like this, with points A, B, and C. If you have a structure that looks like that, with points A, B, and what? And C. Question. Because you need to tell us, is AB, because we shall see AB is a structure, or AB is a gather. Is a gather, because it is strengthening, it is making this stronger. Then SC is also a gather, right? Because it is making the structure stronger. Then BC is also a gather. But now our task is to tell which of them is a tie and which one is a strut. The man has informed us that you begin by pulling out one at a time. When you pull out one, you study how the structure will fall in or will fall. If it falls in, it becomes a gather under compression. So it is the compression forces that are making it to fall inwards. So that one is a gather under. So it is a what? A strut. Now, once it falls off outside, it means that the tension forces are pulling it. So because the tension forces are pulling it, then it is a gather under T, which is a tie. So I remember when I was in senior 2 like you, I used to remember this by looking at this T corresponds with this what? So a tie is under tension. Then S, a strat, it corresponds with a C. So a strat is under compression. Now let's look here. When you remove BC, let's begin with actually AB. When you remove AB, how will these other ones fall? Will they fall inside or they will compress? Are you sure when you remove this, this is going to fall inside like this? How will it fall? When you remove this AB, this will fall this way and this will fall that way. So these two forces that are acting opposite are called what? Are called what? Tension force. So what gather is under tension? So AB is a what? AB is a tie. Are we together? Now let's remove AC. When you remove AC, how will it flow? This will fall inside, and of course this one is already having the support here. So it will be inside like that. Right? Even if this one does not move, but this one will compress it towards that. Are we together? So as long as they are moving towards each other, it is a compression. So what gather is under compression? It is a strat. Are we together? Then let's remove BC. When you remove BC, you remain with this one here. How will it fall? It will fall, this one will fall this way, and that one will fall that way. So BC is under compression. So it is a strat. Example 2 is again ABC, which looks like that. This is A, this is B, this is C. Are we together? Anybody can try this out on board? Patience. I'm seeing your hand up. How many do you want to try? You want to try it there? Patience, you do it here. Evelyn, do it there. Then you man do it the other side and we compare. But I'm giving the microphone to one person. Wait. I give it to you, right? Such that you go back home and give the testimony at church. You will hold it. Have. Yakatela hansi. Bombo clat. I token SCB. Okay.
So guys, we are here. The teacher was explaining that because for me I don't have the support here. So when you come here, when you remove like when you remove like A, B here, this part will fall where? Inside. It is what? It is stress, no so. About stress.
Stress.
We come to AC. AC is here, not so. So when you remove this AC, where these parts are going to fall where? Outside. So it will fall outside.
Remove BC inside strat. It's a strat.
Outside, not so.
This one will fall this way.
This part will be what? To be a tie, not so. So we come to BC. BC is here. When you move like this part here, when you move like, okay, when you move like BC, here we shall remain with nothing. It is what? They will fall where?
This is a
Inside.
start.
So it's a what?
Yeah.
Let us try to analyze the three. Let's give them a hand clap.
Give me my economic. What go and make noise?
So let us try to analyze. You man, I will beat you for nothing. Let's start with patiences. When you remove AB, if you pull out AB, where will this line fall towards? So this line will fall inside there. Of course, let us assume, okay, this one does not fall. So this one, when you remove AB, the remaining one will fall inside. So it will be like this. So two forces towards each other is a compression. So which girder is said to be under a compression? A strut. So here, patience is correct. What if she removes AC? AC is here. When you remove AC, where will the structure fall towards? You see that this, you people are saying outside. Where? This one is going to simply, because it is hinged here, so it is going to fall like this, isn't it? Why do you say outside? So let us assume this one does not move. This one alone is going to move towards this. So it will be like this and this. Is that outside? So when two forces are towards, that is, it is called what? A compression. What girder is said to be under a compression? A strut. So AC is a strut. A strut. Patience. Are we together here? Because if you remove AC, this one will simply fall towards the B, the AB. So it will get compressed. Now, BC. When you remove BC, where will the structure fall? So there are two possibilities now. Do you realize that if I remove AC and there was no support here and here, do you know that AC, this one, this, if I remove SA, I'm removing BC. BC. If I remove BC, this one can fall downwards. Do you observe that? Do you observe that? Now, there are two things here. Coincidentally, this one can move inside. Coincidentally. Do you understand? But now, we expect it to move this way. So if B moves this way and C moves this way, which forces pull away an object? Tension. Which girder is said to be under tension? A tie. So here, patience, you are wrong. A tie. Now we are going to mark the three. We are going to mark the three. Evelyn is saying AB is extra. True or false? She's saying AC is a strut. True or false? She's saying BC is a tie. True or false? Let's go to this guy here. He's saying AC is a strut. True or false? He's saying BC is a tie. True or false? True. Compare. True. Then he's saying AB is a strut. True or false? All right. Now you people will try seeing that structure there. You will try to check whether what we have in the handout is correct. You have a structure that looks like this. right? We have a structure that looks like with the following. This is A, this is B, C, D, E, F, and then G. So your task is to tell us, because now what is holding is the load. Are we together? So you are supposed to tell us what is CD, what is ED, what is BC, what is CE, what is AE, what is AB, what is AB of AD, what is BF, and then is it FG? Yeah. So now I can check out with a few and we see. If you remove CD, Tracy, once you remove CD, this ball is going to continue pulling. Where will the structure fall? Huh? Inside, sure. Because this ball is going to pull this way, right? If it pulls that way, this BC is pulling this way. Which means that two opposite forces acting on the same thing are called a tie. So a gather under, are called a tension, and a gather under tension is called, so CD is a tie. Right? Now what about if you remove ED? When you remove ED, this one here, when you remove ED, this one is going to move like that. This ball is going to bring CD vertical. Okay? Are we together? Christine, when I'm making noise here, your face must be here. I will make sure that I slap you. So when you remove ED, this ball is going to pull CD like down this way. So it will mean D is going to move inside. Then this one is also going to pull CD inside. Right? So two forces acting in the same direction are called. So what is a gather under a compression? A strat. So you will try and see the rest. Materials used in construction. Materials used in construction. Rub off, don't rub the margins. Wait, I will put chalk on your face. Materials used in construction. There are those ones that are ductile. Ductile materials that are used in construction. Remember we said that what are ductile materials? What did we say ductile materials are? What are ductile materials? Kumbe, what is your name? Hajara. What are ductile materials? Evas, what are ductile materials? All of you, what are ductile materials? What are ductile materials? Where is your book? What are ductile materials? Hajar. If me cannot get you, what about the camera? I give you the microphone, eh?
Ductile materials are materials which can be hammered, bent, or ruled into different directions without breaking.
Repeat again.
Ductile materials are materials which can be hammered hammered, bent, or rolled into different directions without breaking.
These are materials that can be, one, hammered, two, bent to all directions that the engineer wants. But the materials cannot do what? Cannot break up. So these are common building materials and have characteristics. Characteristic one, these materials, they should be light. They should be light. They should be light. They shouldn't be as heavy as the majority here. Some of you here are actually heavier than saucepans that cook posho in the kitchen there. So when you fall sick, it becomes a problem carrying you from one place to another. One time I was in class in senior 5 up there, senior 5, senior 6. One of you here came running, but even the running was a problem. She told me, you know, Israel, somebody is dying there. I told her, you go and bring that dead body here. This person, first and foremost, herself is heavy. I doubt whether she can carry somebody. So such materials must not be like that person. Must be like my daughter, the Kalinda. That you can carry her, you pocket her and take her to school. Then too, they should be resistant to chemical reactions. They should be resistant to chemical what? Yeah. That such materials, when you put them in chemicals, they should not react. They should not? Yeah. They must remain intact. Talk about, do you know what we call binding wire? Yeah. Binding wire. When you put binding wire in a chemical, it will remain the same binding wire. Then they should also have a good thermal conductivity. They should be at least good in conducting heat. Are we together? They should be good conductors of heat. Then brittle ones are, how did we define the brittle materials? Materials that a slight bending can make them to break. Materials that when you slightly bend them, they do what? They break, are the ones we defined as brittle materials. Your bones that you have in your bodies are examples of brittle materials. Your bones cannot bend. Any fool that plays around with your bones to bend them is going to make you a lame person. Or is, in other words, causing a fracture. So what are the characteristics of brittle materials? One, it is transparent. Do you know what transparency is? Yes. In light, we talked about 3 or 4 materials. One, they can be transparent, allowing light to go through them. Then there are what? There are translucent, that they allow some small light to go through them. Then they are opaque, that completely do not allow light to go through them. So these materials that are brittle must be transparent too. You're reading like primary kids. Yeah? Can we listen? Keep quiet. Read it alone.
It is an insulator, hence it keeps the room warm during cold days and cold during warm.
This is a Muzungu. So two, the brittle ones at least must be insulators. They shouldn't be in position to conduct heat. Take an example, the tiles that you people use in your houses. One, when you try to bend them, they break. Two, during cold days, when you step on a tile, it remains cold. And even when it is hot days, tiles will never be hot. So you can step on them during the day when the sunshine has terribly shined. And you can even step on them during the times when the when the weather is not a friendly one. Next, my daughter there. It is quite harder bringing the meaning of brittleness. You know tiles, you know marble, you know what else? This material that is used to construct or to repair or to renovate graves or tombs. We have tiles, we have marble, terrazzo, and then granite. They are harder. Next, it cannot be destroyed. Which pests can eat up tiles? I've never seen pests destroying tiles and marble. Lastly, it cannot decompose. You cannot leave tiles there and after 100 years you find them decomposed. They will remain there. They will remain there. So those are some of the characteristics of building materials that are brittle. Now, you people, can't you read through all those ones, the rest? Advantages and disadvantages of using following building materials. One is the tiles, or one are the tiles. We have the grass thatched, and then we have the iron sheets. We have the tiles, we have the grass thatched, and we have the iron sheets. Let's go through them very fast. What are the advantages of using tiles? They are durable. I've told you that when you tile your floor, when you make your floor with tiles, they can take you for a longer period of time. So I hereby advise you, when you grow up and you make money, make sure that your house is tiled. There is a certain sheikh in Kampala there who says that when you find me and you are a failed student that I taught, don't show up to me. Don't even dare show the public that you know me. But now when you grow up and you construct a house, then you tile it, you can visit me, I will visit you. But if you make one grass touched, even when you find me, don't even show public that you know me. I only deal with those people who we are of the same class, same level. But your house is smeared with cow dung. So you want me to come and sit in that house? No. I am a professional teacher and a science teacher. The second one, tiles are waterproof. Tiles cannot absorb water. In senior one, you studied what we call capillarity, capillary rise and capillary fall. When you make the floor of your house with tiles, it will not absorb water from the floor upwards. Neither can it allow water to flow through it downwards. It is waterproof. Water can simply, fall off the tiles. 3. They make the structure look nice. It makes your structure look beautiful. That is why many fools want their graves to be tiled. How can you put money onto a dead body? But my father died, now let's put tiles. Then the disadvantages, they are expensive, that is self-explanatory. They are slippery. Ladies and gentlemen, very many people have died in their bathrooms because of the tiles. Next. The statement is they are not good insulators. However, they are insulators, but not that what? Not that good. If you put water, if you sprinkle water on the tiles, and by mistake it happens to connect with electricity, my friend, you will be shocked. You will be I beg to stop there. You will read through the rest. Pardon? Putting grass on either the floor or the roof. Now, can we listen? Can we listen? I have an announcement to make.